We zoom in. This is the area we're talking about. You can see way down here we have melting, but even back here there's going to be a lot of pressure. That's why we're getting this thrust faulting. We did talk about getting thrust fold areas within the accretionary prism. We can also get a slightly different style of accretionary prism that can have a retro wedge. This is going to affect what kind of faulting and what kind of metamorphism we see within that trench. So here we have an accretionary prism with a 4-arc basin behind it. Here we have an accretionary prism with a retro wedge. There's no 4-arc basin in this case. We have the trench slope break, and then the accretionary prism going down at different angles on either side. So, two different ways that prism can form. Basically, it's kind of like a bulldozer or a snow plow coming and scraping as this goes under. Or if you have a sandbox with a piece of paper that's riding down and through a slit so that you can then pull that paper or mylar sheet, and the sand that's on the paper starts getting pushed against the sand on the other side, you get this forewedge and retro wedge look, just like this. So basically this happened because there was so much sediment on this side, on the edge of the overriding plate, that we get this forewedge and retro wedge. Zooming in much more closely, we can see that it's not a simple fan. We have thrust faults, we have normal faults, we have folds, we have multiple detachments. It's actually a very, very complex structure. So over here, it doesn't really look trench-like, but here's our trench on the ocean side of the fan, and we have trench fill in it. Then we have our high point with slumps and faults, and this is wet sediment. There are lots of earthquakes. It doesn't hold a high peak shape very well. Every time there's an earthquake, things slump and settle. That creates normal faults within that accretionary wedge, with accretionary prism. Accretionary wedge and accretionary prism are synonyms, just two different terms for the same feature. And you can see old thrust faults, older, and newer, and normal faults, and all of this going on. Extensional collapse in the back, collapse in the front, thrusting all over the place. Very complex thing, even though most of the time we just, hey, it's this nice little fan shape. This is really what's going on inside. Here we can see a seismic survey across an accretionary prism. You can see those different thrusts and some slumps and detachments. This looks pretty similar. It's a portion of this anyways. It's not the whole area. But you can see these different thrusts and different attachments and different angles, all of this going on. Here we can see kind of a 3D block diagram drawing of it. We've got these thrust faults. We have some slumping, some normal faults from collapse in the back, right next to thrust faults. We have material moving down and then over and then up as it's bulldozed. Basically think of it as like the bulldozer is to the right here off the page, moving forward. as this plate goes down to the right, and so that material is getting pushed up and around, just like in the front of a snowplow. This zone right down here is called the zone of blue schist formation. So, kind of a fun way to remember, think of Dr. Seuss. Dr. Seuss, in the way he rhymes, we have one schist, two schist, green schist, blue schist. Green schist is formed in continental interiors. Think of continents, green trees and grass, green schist. That's not why it's green, just good memory tool. So continental interiors, we get green schist. This is metamorphic mafic rock from volcanic material. Out in the ocean, at the accretionary wedge, we get blue schist. Think oceans in blue. This is metamorphic glaucophane. It's a blue amphibole, and it forms in the accretionary wedges, which are full of sediment with a little bit of basaltic material mixed in, pressure and temperature, and we get blue schist. So green schist, continental interiors, blue schist, accretionary prisms, accretionary wedges. So again, that's right down here, kind of in the deep, high pressure parts of that accretionary wedge. Melange, on the other hand, a nice French sounding word, melange, is a chaotic mixture of lots of different rock types. You can't see any bedding, there's no layering. This is what a lot of that accretionary wedge is made of. If it hasn't gotten metamorphosed into blue schist, most of it is just melange. Sediment of multiple types. There's clay, there's limestone, there's basaltic material, there are rocks, there's dust, all of it just chaotically mixed together. Now, a forearc basin in a volcanic arc. We talk about these quite often when we talk about subduction zones and collision zones. One question is, why are they always arcs? Why aren't they straight lines? Why are they forming in the first place? Well, at the top of the accretionary prism, there's an abrupt decrease in slope called the trench slope break, and behind it we get a basin. As it tapers away, there's that forearc basin. After that, inside a ways, we get a volcanic arc. This is a chain of volcanoes that forms over the surface of oceanic lithosphere that happens to be the overriding plate. So what's the mineral makeup of these volcanoes? Are they mafic? Are they intermediate? Well, they're intermediate. So the question is, why? How are these volcanoes intermediate in composition? We have this downgoing lithosphere plate, we have an overriding plate, and we have magma coming up. This magma is thought to be a mixture of some melted downgoing plate, lots more of melted material from the bottom of the overriding plate, and it's melting because this downgoing plate is wet. This oceanic crust is full of water. Basalt is commonly quite porous, It has fractures, it has vesicles, it has lots of places that contain water when it's the ocean floor. You stuff that down into the interior of the earth as it's subducting. That water is heating up, escaping as gas or super high pressure hot water into the material above it, because water is definitely less dense than rock, so it's trying to rise. As it's rising and mixing and interacting with that hot rock above that subducting plate, it causes melting, because rock with water mixed in melts at a lower temperature than rock with no water. So it's changing the melting point of the rock that it's entering. Therefore, that rock can melt even though the temperature did not change. That rock melts, that makes it less dense. It's buoyant, it's rising. So this is that rising magma. As it rises, it's hotter than what it's going through because it's rising relatively rapidly compared to temperature gradient within the earth. So it's picking up material as it's rising, as it melts rock that it goes through. And a lot of times, because this is a compressional zone, it can only rise so far, and it can get stuck. But it's still hot. It still brought a lot of heat with it as it rose through whatever cracks it could push through. Therefore, it heats up the rock around it, which can basically melt the rock above it, which then starts rising. It'll rise until it can't, and it can melt the rock above it. So a lot of times, the magma that actually ends up reaching the volcano and becoming lava isn't the same magma that started way down here, down deep. Down deep, it was very mafic. But as it moved up, it both picked up material as it moved through the crust, and sometimes gets stuck and just melts crust, which then rises. Therefore, the stuff that reaches the volcano to actually come out has lots and lots of continental crustal material in it. Therefore, it's felsic to intermediate. It's no longer supermafic like this material way down here. Now, our subducting plate and overriding plate can interact in a couple of ways, depending on the speed of the two plates and the speed of the rollback. So this plate, the subducting plate, the plate itself is moving to the right, but the rollback is changing where that flexure is, where the contact point is, moving that contact point to the left. We call that VRB, velocity of rollback. Here we have velocity of the overriding plate. It's moving to the left. If the velocity of the overriding plate is faster than the velocity of rollback, we get something like the Andes Mountains down in South America, where we have the velocity of the overriding plate is faster, so we have our accretionary prism that has that retro wedge on the back of it. We have a lot of volcanics forming with melting and rising and partial melting, and we get andesitic intermediate volcanoes. And on the back side, we have uplift and full thrust belts, because that continent is trying to move faster than that rollback. Therefore, it doesn't have anywhere to go. It creates compression and uplift. On the other hand, we can have something like we have in the Marianas Trench area. Here, the velocity of the rollback is greater. So this rollback is moving left faster than this overriding plate is coming. This is causing tension. It's causing stretching. Basically, this part has to move left faster than it's being pushed from behind. Therefore, it actually causes stretching. It causes tension and extension behind that volcanic arch. It's called a back arc basin because it's a basin caused by stretching behind that volcanic arc. And this happens because the rollback is faster than the incoming plate. We can actually get new oceans or seas forming if that back arc basin gets enough extension, starts creating a new mid-ocean ridge. We can get a whole seaway going on that overriding plate simply because the rollback was faster than that plate was coming. On the other hand, we can have a case where it used to be faster and now it's more equal. Or a case where it used to be faster and now it's moving in a different direction altogether. So, we can get different changes occur. Rollback still happening, but in the past, the overriding plate was either going in a different direction or going more slowly, but now is going in the same direction and the same speed as the rollback, so the extension has stopped. It's an extinct ridge. Up here, it was a spreading center, mantle material coming all the way up to ooze out of that extensional center to create new oceanic crust. Down here it's stopped. It's no longer buoyant because it's all cooled down. It's all older. The mantle no longer comes up to the surface. It's cooled and thickened because there's no more spreading. This should have been... Oops. Let me fix this. This is an equal sign. So the rollback and the overriding plate are moving at equal speeds. So there's no extension and no compression. But in this case, in Japan, there's an extinct ridge because there used to be extension. Now, the back arc region, behind the arc. If we move up here to the Aleutian Islands, up in Alaska, we can see, it's a nice curved arc of islands. And behind it, we have the Bering Sea. We have some continental shelf, the shallow sediment-laden area. And then we have some ocean floor, but it's trapped behind the Aleutian Islands. This ocean floor is completely different age than the stuff out here. And it got trapped and stuck there, and it's going to be there for a long time until something on the far side of the Pacific Ocean, due to, if subduction continues long enough and stuff comes along and slams into it and compresses all of this. Otherwise, that ocean floor is going to be there for a very, very long time, just trapped behind that volcanic island arc. Not subducting, just sitting and hanging out. The reason they're curved, they're always curved, is because we're dealing with a spherical surface. The surface of the Earth isn't flat like a map. You can kind of see this experimentally if you take a ping pong ball, make a straight little cut, and then push in on one side of it. You had a straight cut, but as you push it in, the edge of this indented area is going to be a curve. And the edges past where your cut were will tear a little bit if you're pushing pretty hard, but they'll tear in a curve. So even if you try to make a straight line, it ends up creating curved edges and curved surfaces because you have a spherical surface, you're pressing it down and in, but you can't change the surface area. Therefore, it has to flex and pucker and curve. And this is how we get, as this plate subducts and goes under, this area over here is curved, and we get a curved volcanic arc. And we get curved accretionary prisms. So here we can see this subducting plate, and we can see as it's diving down, it gets curved, and our accretionary prism is bowed. And this is where we get these curved island chains, these curved volcanic arcs. So here's a map view. This plate here, down going, it's moving west. You can see a north arrow here. So this plate is moving to the west. Here's our accretionary prism. Inside of that we have a volcanic arc, and it's curved following the shape of that flexure. To either side of it, we're going to have strike-slip faults. They may not, be as long as shown here, but on the edges of this curvature, we'll have strike-slip faults. It's the only way for the plates to interact with each other without creating or destroying mass.